Our first tutorial today is by J. Michael Burgess, and J. Michael Burgess is joining us from MP, that's right.
Mhm.
And we also have Bjorn Blitzinger, who is also at MPE, a PhD student who's going to be helping out in the chat if you have any questions during the instruction. So take it away, J. Michael.
Okay. Hi, everyone. So welcome to the tutorial. So there's a link in for the binder that's in the repo. So if you're not familiar with binder, if you click the link, it should, I've been testing it all morning. It should, after a few moments, load up basically what looks like a Jupyter Notebook environment. And then it has the full, all the bells and whistles 3ML environment loaded, and you should be able to execute the notebooks. If you installed it locally, then you should open up, depending on how you installed it, if you went through and used the Docker, then you should run this command, and that's where you have also cloned the repo, and you should see the notebooks there, so you can follow along locally. Or if you actually installed 3ML with Conda or pip, again, just open up a Jupyter Notebook server and you can follow along. But if there are lots of problems with installation or anything happened, I know there were some problems with the Conda environment earlier in the last 2 sessions, just let me know. You can still follow along here, and I'm always available on the GitHub if there are issues. We'll try to get to those as quickly as possible. And just shout out questions, and yeah, Bjorn is there to help with the chat. So the first thing that I want to do is just kind of introduce you to the basics of 3ML before we get into X-ray analysis, because 3ML is not just focused on X-ray analysis. There's a lot of us do gamma rays and X-rays. There's a lot of focus on that for the X-ray plugin. But just since it's kind of a new system for some, I want to introduce a few of the concepts, how to this is reversed in the actual order, but how you build models with Astro models. So for us, we're just going to focus on spectral models, not extended or spatial models at the moment. And how do you create a plugin, what a plugin is, how you do fits, and then how you save the results of those fits and manipulate them later for analysis. Cool. Any questions before we get started?
I have a basic question about binder. Just, do you ever have to install libraries there, or is it your binder is made so that all the libraries that you need are already there?
So I built a Conda environment. I just put in basically a YAML file, which is very similar to the one that's listed here for the Conda environment. And then binder will build a Docker in the background and store that Docker in a cache. So if it hasn't been preloaded first, then it takes a while because it actually has to build the Docker, and doing things like installing expect models takes a long time, but it should. Otherwise, it just pulls it from a cache. It'll say like found built image, and then that's all you have to do.
So anything that's pip installable should be available on binder.
Anything that you put in the repository in the requirements.txt for pip or environment.yaml for Conda should be completely available.
Awesome, thank you.
Mm-hmm. So yeah, hopefully I just tried to launch one again. It's taking a little bit of time, but just let me know if you get behind or have any questions. Yeah, it is slow to start up sometimes. Okay, so first plugin we'll focus on, or the only other one besides the X-ray one at the moment, is just a simple plugin called XY-like. So a plugin is just an interface between data and a model via the likelihood. I won't go over constructing your own plugin, like building one from the base class, but just to give you a few ideas here and like just do an entire overview of 3ML, we'll just use a simple XY-like plugin. So I'm running locally on a cluster, so it's going to be run a lot faster than the binder. But yeah, to import 3ML and Astro models, you just say from 3ML import star. It's not the safest thing to do all the time, but this will give you all the models from master models, spectral, spatial, etc., all the plugins, a lot of the little features. And if you're curious, you can always go look in the init file and see the things that are loaded. These are just some things I put in here to set up the style, and just a little function to style the plots. Nothing really fancy there. And then we have a lot of test data in 3ML, so you can, and that's what this does, is just pulls this out of your install, and I'll be using a test data set that we have constructed for this XYLite plugin. So that's just a path to a data file. And the XYLite plugin, again, it's a very generic plugin. It's designed to fit either Gaussian or Poisson distributed data, depending on what you put in. It can read from text files and stuff. It's something we use for demos, and so there are a few advanced plugins that are built off of it, but you can use it kind of just as a generic interface to very simple data that the likelihood is simply Gaussian or Poisson, depending on what you tell it. So here I've just loaded up some this data from this test data file, and it's simulated power law with Gaussian distributed errors. The XYLite plugin can plot itself, so you just see XY, power law, and Gaussian distributed errors, nothing fancy. It knows that the data, if it's Poisson or not, which allows it to choose its likelihood. It has access to its data. There's nothing really fancy about this plugin. But the main thing is that it knows right now, all it knows about itself is the data, but it will, when we pass a model to it later, a likelihood model, it will know how to connect that model to the proper likelihood, and then it will be able to pass the model into the data to compute the likelihood value. Any questions?
I have a question. Again, how does it know that it's Poisson or not?
Right. So it has a text file format. So if I were to do the help function, hopefully this works here. Yeah, it tells you basically like what the text file format has to be. It can also read from like pandas. It knows if you don't insert any uncertainty on Y, it assumes that it's Poisson data, or there's also a flag you can pass in the main constructor. So so if I were to do the help on XYLite here, you can see you pass X, Y, Y error. If no Y error is passed, it assumes that you're passing Poisson data. Exposure, which is something used by other things, and the name. And also, yeah, that's something else that say clearly. Every plugin needs to have a name so that its data is distinguishable when you're doing your fit. So here I've called it XYLite. But yeah, does that answer your question?
Yes, thank you.
Okay, so that's just a simple plugin, again, holding its data. But to do anything, we need to create a model, and so that's what Astro Models is. It's again, it's a secondary package, lots of documentation over on the thing. There's a lot more than I can go into in this demo, but it is what we're going to be using it for is just doing spectral functions. So you can see a list of the functions if you go. There's some. If you go into the built-in models in the documentation, you can see some of the models that are included in Astro Models already. We're always adding more, but most of the basic kind of like power law functions. There's also some absorption models now, like TBABs and WABs and stuff like that, that are natively coded in 3ML. And you also have access to all the expect models, which we'll get to later. But for now, we'll just make a power law. So we just instance an object. So here, call it power law with a name. And if we look at the display, we can see what's going on here. We have a name, the LaTeX formula. Some functions don't have that. And we see all the parameters and a description of the parameters, such as their current value, description, min, max value if they have one, the unit if it has one. It just depends on what people specify when they create the model, and et cetera. So that's, right now it's just a function. The way you interact with this function or the spectral shape is through accessing attributes. So any of the parameters you see here, they can be accessed by saying dot attribute equals 1. You can also say dot value, but that's not really needed. So there's also this like pivot energy here, which is by default not free. You can set its value. You can set the bounds on a value by passing a tuple. So here I'm saying the minimum value is -3, but it doesn't have a maximum value. Or you can set the max value explicitly. You can free and fix functions. So if I said free equals false, then it would be fixed. Or let's say fix equals true, it's fixed. So that's just a Boolean. So we do that. We can interact with it, and then it would change the description here. And then to call the function, so you just call the objects. The object call is an like doing f of x. So if I were to do this, just make a loop where I change the index, you would see that now the power law and log space is looping through all these index values. So and all the functions are by default. The spectral functions assume unless, which we'll get to later, once you pass this function into the likelihood model, they're all assumed to be in keV, and the output is in photons per centimeter squared per second. So designed by X-ray people, so that's why the units are what they are. Now, we take a function and we need to pass it to a point source. So for the XY like, we treat everything like a point source. So this is the next part in our model. And you'll see once we get going that we're actually building up a tree. So point source, we have to give it a name. You specify an RA index. These are going to be parameters in the model, but they're not free unless you say they are, or unless you have a likelihood that uses the RA index. So I just put them to dummy value of 0. And importantly for us, we pass a spectral shape, and that's going to be our power law. And if you, after that, you print it, you can see now you have your source, does its position. So it's right ascension into declination. There are other ways to specify this. You can look in the docs, you pass astropy coordinates and stuff like that. And then you see the spectrum. So the spectrum, since there can be multiple components to a spectrum, you'll see the first thing is the main thing, which will be if you have an additive model, if you can add together, which we'll see later, spectral components. If you want to do a power law plus a black body, you would just write out the algebra for that, either when you instance the object, or you can do it with the objects themselves. But yes, you'll see now that our point source has a spectrum. It's our power law, so it's the same kind of thing. You can do a lot of things with point sources. One of them is you can see what the free parameters are in the model, which should return a dictionary with the model parameter's name, well, the point source parameter's name, and then the parameter with its values, etc. But one thing you see here is now you have this mySource.spectrum.main.powerlaw.k. So this is kind of the tree structure that starts forming when you're building a model, which is sort of what the logo is trying to let you know here, is that you build up this tree structure when you're getting ready to fit. So that's why you do this, and that's how you can actually access the parameters. You can do it with strings in a different way, but if I were to do this right here, I would actually return the value of, or I would return the parameter here, which is k, and you can see its units, its min max value, some of the same kind of things that I would get if I were to have just done power laws. I would get the same thing, except for now that this same object is attached to that point source. Okay, so we're not going to add any extra point sources, but we could, if we had a model that had multiple point sources or extended sources or neutrino sources or something like that, we could start building those. And then when we get done, we pass all of that to our likelihood model. So I'm just going to pass the point source, and you would just do, if you had more, you would say comma, that, blah, blah, blah. We'll get to that in an extended tutorial later. And then we can look at our model. Now the display starts to change a bit here. We see the number of point sources we have. No, we have no extended sources. See our free parameters, this table here. And again, we would see there's some fixed parameters. You could do similarly .display, and it would return the same thing. And if you said complete equals true, then you would see your fixed parameters. If you had linked parameters, independent variables, some other things you can do in building models. So that's pretty much it when we get to building models. And you would access, if you wanted to get your point source in this model, since I called it, I don't remember what I called it at the moment. Oh, my source. You could say my source, and then you would return your point source there. So if you have multiple sources, that's how you would access them in the model. Okay, so we have a model, we have our data. Now we need to make a likelihood, which is by combining the plugin and the model. Now, if you're just doing a quick analysis and setting it up, you won't have to do this manually, but I'll do this just for you to get an idea of what the plugin's doing. All plugins have this function called setModel, which passes that function. If you're designing a new plugin, would tell 3ML how the model should interact with the data and interface to so that the plugin can read the model and translate it into the data. So I do that here. Now, when I call getLogLike, which is a function every plugin has, okay, it's compiling on number there, but now I can get the log likelihood for the current parameters. And if I change, for example, the index on the power law model, I could have done this on the model itself or on the point source because they're all sharing the object. I call it log like again. Okay, the log likelihood has changed. So if I do this now directly on the model, again, the likelihood has changed. So that's how, so now the plugin knows about the model. And you can imagine if we had other plugins that were running Fermi-Lat software or doing optical software or whatever, if they all know about the same model, you change the parameters, they all get their all different likelihood values. And this, of course, the log likelihood gets summed, and that's how the plugins talk to each other, is via the likelihood. Okay, so now let's do some fitting. So you can do.
I can ask a question. You said a couple of times that there could be multiple sources in a model. Mm-hmm. Is that if you were to fit multiple sources like at the same time, and you know they're all power laws with the same slope, let's say, or is it if like would you use that if sources are not resolved, you fit, let's say, two instruments and Chandra resolves them and Fermi does not?
Yes, you could do either of those combinations. So we'll do an example in the, hopefully we have time for the advanced topics, where we just have two X-ray point sources and we have two different data sets, but we want to link some parameters. So you could do that. So one of the ideas is like where this came from is like with Fermi-Lat. If you had to fit the diffuse or the galactic, you want to fit an extended source for the galactic plane, but you knew you had some point sources on top of that. But all of this is present in the X-ray data and also the Fermi data. You could add your point sources and assign them to a certain plugin, because those plugins can assign sources, and then do your diffuse source only in Fermi, but perhaps again, the diffuse bleeds through into the point source or something like that. I mean, I'm just making up off the top of my head a situation, but yes, you can do that or something else. Another example is with Fermi-Lat. There are sometimes multiple point sources all within the field of view, and you can fit them, and they're because its resolution isn't great, you can fit them all at the same time, because whether it assigns that the photon going to this source or that source it doesn't really know, so you have to kind of fit all the things at the same time. And if you want to see an example of that, if you go to the documentation and go to the Fermi-Lat example, it actually, the dark mode doesn't look great there. It actually goes through this where they're fitting multiple point sources at the same time. So they're fitting this pulsar, crab, whatever this is, and they do the optimization on all of those point sources at the same time. Does that answer your question?
Yeah, thanks.
Mm-hmm. So here we just have again, just a single point source. So the next step after you've made plugins is you would pass them to this object called a data list. And so if I had more, I would just say, you know, my X-ray plugin here. You can do list comprehension, whatever. And that is just a container that holds all the plugins that you want to use for this analysis. And if I was doing a maximum likelihood fit, then I would grab this object, which is called joint likelihood, and I would pass my model and my data list. And by default, it's set up to use minuet as the minimizer. And if I want to fit, I hit fit, and we're done. This result is actually just another pandas table. You can turn off if you want. You can say quiet equals true. If you're doing 1,000,000 fits, then it would just fit and you wouldn't see anything. But that's about it. You'll see the optimized parameters, the covariance matrix, the total likelihood, which for us, since we only have one plugin, it's the same. And these statistical measures, if you're interested in using these, like information criteria. If you wanted to use the SciPy minimizer, there's a couple of minimizers available. There's another interface where you can actually set the minimizer. I could do this by saying SciPy, or I can build one of these local minimizers. And again, I encourage you to go look at the documentation on all the different types of minimizers you can use, because we don't have the time here. But yeah, if I wanted to use SciPy, again, I can redo the fit, and I get about the same answer. So that's how you do maximum likelihood estimation. Okay. But we want to save, there's a lot of information that's saved in the fit, and we'll go over that again in just a moment. But just so we don't lose kind of the flow, let's see what we'd have to do if we wanted to now switch to doing a Bayesian fit. Perhaps we wanted to compare the approaches or whatnot. So there's actually pretty much nothing different between doing a maximum likelihood fit and doing a Bayesian fit, except for now we need to set priors on our parameters. So we have several priors: log uniform, uniform, Gaussians, truncated Gaussians, Cauchy, I can never say that right. You can go look in the documentation, see what's available. You can always add more, and you can make some that you can make them local. But to set a prior, you just call your parameter, and you say dot prior equals whatever you want. So log uniform, you need to set the lower bound, the upper bound. I'll use an informative prior here because uniform priors are never great. So I've just put a Gaussian with a mu equals -2, sigma equals 2. And just so that I won't complain when I'm running this, I'm removing the bounds in the power law index because the Gaussian is unbounded. There is a truncated Gaussian available as well, but it will complain if I set that the bounds are, you know, -3 and +3, and it tries to sample out there, it will fail on me. So I set priors. Now, if I were to now go look again at my model, I believe, no, you won't see it there, but you can go look at, I won't remember. You can see that you have priors set, but also it will warn you if you try to do a Bayesian analysis and you haven't set any priors yet. Now, to do the Bayesian analysis, just like with the joint likelihood or for the maximum likelihood approach, I pass my model, my data list, assuming that I have prior set. We're all good. You need to set the sampler. So I do choose EMC here because I have that installed. And then you call Bayes.sampler.setup so that you can pass, because the Bayesian samplers have more configuration. So I've set the number of walkers, the number of warm-up steps, the number of iterations. It's set. And then very similar to doing .fit for the maximum likelihood, I say .sample, and then I can plot the plugin afterwards. So we just run the warm-up and then the actual iteration. Again, we get our kind of output here telling us our parameters. Now we get some more information criteria because we did Monte Carlo sampling, like the DIC and the effective number of free parameters. There's our fit to this likelihood. If we wanted to switch to multi-nest and we have multi-nest installed, we could say, okay, I set my sampler to multi-nest, do setup, number of live points. You could pass all the other parameters you need to multi-nest here if you wanted to. Just go read the documentation for that. So now it's set to multi-nest, run multi-nest, and our fit is done. Again, we get just our the estimations of our uncertainties. and our Bayesian fit is done. Okay, that's how you do switch between joint likelihood and Bayesian analysis. But what about the results, the samples? How do we get the uncertainties from our fit if we want to manipulate them? We don't want to go and copy and paste this and write a parser or something like that. So the joint likelihood in the Bayes objects that we created earlier, when we're done fitting, they'll have this dot results thing. So we're going to extract that. And if you want to look at what's in that object, it's basically what we got when we finished our fit. So we see the map point, all this information. Since we did it, the last thing we used was actually multinest. We also get the log z there. And the Bayesian result thing can also do corner plots because it's Bayesian answer, and you have to have corner plots, of course. And similar to if we were to look at the what did I call it? MLE results, right? MLE results, if I wanted to say display, then you would see the results we got from the fit. You could also look at, it saves a copy of the model at the, you could also get the covariance matrix, which is just a matrix. There's a thing called optimized model, which will always be there. It's just like the model that we made for with the free parameters, except for that you can never change this so that you know what your maximum likelihood value would be. So it's just another object. So there's a whole lot. You can always do tab completion. There's a whole lot of things that this does. But for the sake of time, we'll move on to some of the things that are important. So if I took my Bayes results, and this is going to be the same between the maximum likelihood and the Bayesian thing if we want to get uncertainties on parameters. So I wanted to, for example, get the equal tilde interval of a parameter. I would pass the path in my model. So you can see up here the path down the tree as a string. And I could say my confidence level. I pull this out and it would just return a tuple, which gives you the upper and lower bound for the equal tilde interval. Similarly, if you wanted the highest posterior interval, which may not be equal on either side, you could do the same thing and it returns the uncertainty there. If I wanted to get the flux, the integral flux of the model from, let's say, 1 keV to 1 MeV at confidence level of 0.68, I would just do this. It propagates the uncertainties and it returns a pandas table with, again, there's only one point source, but it could do, which we'll see later, it can return the total propagated flux, upper and lower bound. It could return also the independent point sources. If they had multiple spectral components, etc. And that's just a pandas table, and the thing inside is actually an AstroPi units quantity, so you could do things with units. If I wanted to plot the spectrum of the fit from, again, the Bayesian result, I can plot it. I specify the flux unit, so I say here I want ergs per second per keV per centimeter squared, and I want my confidence bounds to be 95%. It's going to propagate all the uncertainty, do your plots. Another fun thing is say that I want to do error propagation with some complicated function on my own. You can do this thing and return an object which we call a random variate. And again, you just get the results, you pass the parameter, the path of the parameter that you want to analyze. So you get your index. When you press index here, you'll see its display is the equal tilde interval and the highest posterior HPD interval. And that's because this object knows about its uncertainty. It's sort of, it knows about the Monte Carlo samples that were used to derive it. So that means that if I wanted to propagate the index into some complicated function, I just chose sine plus 4 here to do that. And this thing then carries around its uncertainty from the index. So if I were plus 1, you can see that it just continues knowing about its uncertainty. It also knows about its median, its mean, etc. So that's random variates. That's documented in the documentation. You can see some of the stuff that you can do with that. But okay, this is great. But then I close my Python session and I lose all this information about the fit. So what we want to do is save these to disk. So, and again, this works with MLE, R-based. I would write this as a FITS file. There's also an HDF5 format that we have. They're all similar. You can see in the documentation how to switch between the two. And then if I want to load the results from a FITS file, I would just say load my results. And then you see all this information that I had about the fit, the covariance matrix, the samples, the model. It's all live again, and all the operations that I just did where I was doing error propagations, it's all there. For example, look at the samples from running multinest. You can see this optimized model again. So all the information about the fit is serializable to this. So you could pass this to a journal if you wanted to make sure that your results were reproducible, etc. So that's the basics of kind of the general workflow for 3ML, which took longer than I hoped. But yeah, so before we move to X-ray analysis, now you just need to learn about the plugin for X-ray analysis, and all of this stuff will apply. So before we do that, are there any questions?
I have one question, if that's okay. When you serialize to the results you were just talking about, does that include the data as well, or is it just the fit results?
Just the fit results at the moment. So you could rebuild your plugin you can make a plugin and then take the clone the model. So I'll show this later. You could clone the optimized model that's there and then pass that back to the Bayesian analysis, and it will reconstruct everything. But yeah, so that's a good point. We're working on a way now to be able to serialize the plugins as well, so that you could basically pass a file type and you have the entire analysis there. But there are lots of different plugins, and so it's a bit difficult to do that, and we're trying to find the best format to do that. So if there are any ideas for how to do that, it'd be great. But at the moment, you can't serialize the plugins, but it's something that's being worked on in an experimental branch.
Thanks.
Mm-hmm. Okay, so now we'll move over to the second notebook, which is the X-ray analysis. So, so I don't know very much about Chandra data. I used some demo responses to make some simulated data. So if it looks very weird to you or the science cases don't make any sense, I apologize for my ignorance ahead of time. So the plugin that we'll be using to do X-ray analysis is one called OGIP-like, which just stands for the OGIP format. And it's a plugin that's basically, it's a subclass of the more generic dispersion spectrum-like, which is a plugin that handles bend count data that has energy dispersion, so a response matrix, which is built off of another plugin and another plugin. There's a pretty deep hierarchy here because there's you have all the way down to just a regular histogram plugin. But OGIP-like, what it basically does is allow you, instead of passing these objects that have the bend data and the generic response, you can read in plugins, or you can read in FITS files that are in OGIP format. So you can do, just like you would do in other programs, you can pass, if you have multiple spectra, you can pass file name with the braces number, or you can specify the spectrum number directly in the OGIP-like constructor. So let's just have a look at this. I made some simulated data. It's in the folder, in the binder, and also in the repo. So again, the first thing you need to always do is name your plugin. And your observe file, so your PI file, or the data that has your total counts, you pass here. If you have a background, if something like Swift-BAT, where the background is modeled because it's a coded aperture instrument, you could just say none. You can also pass other things, which we'll talk about in a moment. And then you can pass your response. If your response, like it's an instrument like GBM, and the response and the RMF and ARF are already combined, you would just pass that. But if you have an ARF file, you would just put the path to that. And here, I just have one spectrum in there, and so I specified the spectrum number. So I do that, and the first thing you'll notice is this auto-probed noise model. So what we do is, as long as the headers are correct, we make sure that, so here we have the observation is Poisson, the background file is Poisson. So we automatically go through and choose the correct likelihood for you. You could hack it and switch to a chi-square likelihood, but of course this will screw up if you have 0 counts in a channel. One thing we wanted is to make sure that the plugins that you don't really get this choice of switching to a likelihood, because it will lead to improper results. And some of the minimizers will actually crash compared to regular Levenberg Mark Quad if you use the wrong likelihood. So that's kind of enforced. There is a way to change it. If you want to know how to hack it, you can open an issue on the GitHub. But for now, we will select the proper likelihood. So we have this plugin. It has some attributes that let you access the data. For example, you can, this is the Lien-Ma significance. So from the Lien-Ma paper 1983, that's the total significance of the observation. You could look at significance per channel. You could display the response, just the Chandra response here. You could look at the exposure, which is just for the simulated data 1 second. And then you can view the count spectrum. So here you see my attempt at making some simulated Chandra data, the total spectrum and the scaled background. But if I wanted to look at the unscaled, so all the scale factors and exposures, I'm done. Say scaled background equals false, and you would see that background is quite bright compared to the source. So that's just a little helper thing, so you can see your data. If you want to now choose which measurements that you want to use, what channels you want to use. So we tried to make this mimic a bit the XSpec output, or at least for people that are familiar with that. But there's a lot of ways that you can set channels. So I encourage you to look at the helper function, which is for this, the help function for choosing the channels, which is the set active measurements. There's a lot of details on all the different things that you can do. You can choose combinations of energy and channel, etc. That just read the documentation here. I'm just going to say I want to fit between 0.2 keV and 10 keV. So I set my active measurements. It'll tell you what the channels translate to, and hopefully, yeah, in my display, the deselected channels are kind of shaded here, and you see the parts that you actually want to fit. Since we're at the moment, we don't have a background model specified. We'll talk about that in a moment. But you always want to have, at least for any of the profile likelihoods, for them to be valid, you always need to have at least one count on the background. Click on that link, and there's an interesting thing done by Giacomo on this. So I just would say, okay, I want to rebend on the background, and it'll tell you how many bends I'm using. And you can see the rebend spectrum. You can also rebend on source. There's lots of stuff. You want to remove the binning, you just say remove binning. You can do a lot of things there. Okay, so that's some of the basics of interacting with the OGIP plugin. There's other things that you can do. Always use tab completion. Go look at the source code and see all the different functions. But that's the basic interface to X-ray data. So now if we want to fit, I just kind of give an example. I simulated a black body in this this data set. So I pull up a black body here. I'm gonna, for now, just fit Bayesian because that's what I like to do. So I put some a log uniform prior, I put a truncated Gaussian on the temperature of the black body because I don't want it to go below 0. Also, and you can try this on your own, if you have XSpec installed and you follow the instructions for linking the two, you could also choose now to load the XSpec black body. So the XSpec functions are all denoted by XS, and in the binder and also in the Docker, XSpec is already preloaded, or if you install from the cond environment, it should all work pretty seamlessly. But that's always, it's always sometimes a tricky thing. So we specified our spectral model. I'm going to call my point source a white dwarf, and don't care where its location is at the moment, and pass my spectral shape just like I did with the XY-like plugin. There's nothing different here. And yeah, you can see our parameters. I pass it to Bayesian analysis. Now, another thing we might want to do is look at the prior predictive checks. I think this was discussed in the XA tutorial as well. This is going to be coming directly into 3ML at some point, but right now I have my own repository called PPC. And so if that's installed on the binder and the Docker environment as well, but you would just import that, install this package, pip install it, and you grab this function compute prior PC. You would pass your analysis, the number of simulations. Yes, yeah, you can do multimodal components. So you can do this in several ways. This is, if you look at the Astro models documentation, it's they show like you can pass them as components, which are separate objects, or you can do additive things. For example, if I wanted to say, which we'll get to in a minute, black body plus power law, I would do it like this, except for now. Yeah, that's why it's failing. Yeah, so if I did that, what you will see is that now the parameters get indexed by the order in which you enter them. So now the black body's amplitude, K here, is _1. And then the same thing for the temperature, and the power loss parameters are _2. So that's how you do an additive model. If I wanted to multiply them, I think the units won't work out here, so it might complain. No, it's fine. Oh yeah, it does something funky there. So you can do all kinds of different combinations of algebraic combinations of the functions. So for example, if you wanted to add on an absorption feature as well, but we'll get to that in a moment. So here, yeah, just reload our model. Yeah, so if we want to do prior predictive checks, we specify a file name, overwrite, and here I'm just returning the PPC so you can see it. Oh, actually import it first. So it's going to go through and it's going to sample the prior and generate a bunch of fake data. And then we can look at that over plotted. You're welcome. Yeah, we can look at this is just 1, 2, 3 level uncertainty. Our prior choice over plotted with our data. So the data are in yellow, the simulated data are these different confidence bands. You can go look at the documentation for how to play around with these PPC plots for prior predictive checks. But that's just something you can do to make sure that your prior range is not insane before you do a fit. You can also choose, I won't do it here for time's sake, you can also choose to just manipulate one parameter with its prior and do the same kind of plot. So now, since we're going to do a Bayesian fit, this time I'll choose UltraNest to do this. So I call it, I set set up its parameters. And just like we did with the XYLike plugin, I say, okay, let me sample. And again, in the binder, I think this is going to take a lot more time than it is on this computer. But sorry about that. But if you install it locally, it should run pretty quickly. But you can always go back and I'll leave this repository open for a long time. You get some of the output from UltraNest, you see, and you get the same kind of output that we got with the other plugins. And again, just like with the XYLike plugin, you can save the results. You can do a corner plot. There's a helper function, so the plugins themselves can actually the OGIP plugin can display its counts along with the model when it's done. But sometimes your analysis might have several X-ray plugins. So like with Fermi GBM, we always hit multiple X-ray detectors or gamma ray detectors together at one time. And so we want to see those overplotted. So that's what this helper function, this display spectrum model counts is. And so you see, here's the background, here are the residuals, the model in the folded data space. And I binned it up just a little bit. This min rate sets the binning. There's a lot of different things you can do there. 3ML, so you see over here in my text editor, I have this YAML configuration file. There's a lot of configuration. I don't really have a lot of time to go over all of that. But you can always go and look at all the different configuration options. So like one of the things, if you want to change how these plots look, by default, you can always do show configuration. It shows a tree with all the current settings and the options. You can always, whenever you load 3ML, you'll get this object called 3ML config. It does tab completion, and you can go through and set up what you want for the global configuration. You can always pass these options down to the actual functions if you want, but I like to just configure things so that it looks nice on my computer. This is just one of the things you can configure, which is the display here. So again, this is just the model, fitted model folded through the data. Now, if we wanted to switch and fit a power law to this instead of a black body, that's basically what I've done here. Again, set up, just to make this fast for now. Again, set up and with a different Bayesian analysis, go through once again, set priors, use ultranest, and then see how well the model fits to the data. And you see, okay, it doesn't look really great because I actually simulated a black body for this data. And then just like we did with the XY-like plugin, I can pass each of the results objects from the analysis down to this plot spectra function. The arrows will get propagated, and we can see the here, was it fnew? Yeah, or yeah. I specified, yeah, here fnew. I could have done new fnew by just changing the units. And we can see the uncertainties from the fits and the two different models. Could have also said joules. You can use any AstroPi unit, whatever you prefer. So yeah, that was the fit to our data. And now if we want to do posterior predictive checks, where it's the same as the prior predictive checks, except for now we want to sample from our posterior directly. This will allow us to do some model checking, just sort of like with residuals. So I could do this with, first for the black body fits. Which again, I think this takes quite a bit of time on the binder. So if it gets stuck there, you can just stop it and move on. And done. And I can then do the same kind of plot that I did earlier. I can subtract the background just for visualization purposes and see from my fit if it looks nice. And it looks like the posterior can generate data that sort of look like from the model that we fitted that sort of look like the data. This is not very informative. So the real data is in yellow again, and these are the 1, 2, 3 sigma, or sorry, the way around, 1, 2, 3 sigma uncertainties from the posterior, pass back through the likelihood. Another way to look at this is by, again, looking at QQ plots, where you basically do an integral along the model and real data channel access. And you would want to see a one-to-one line here. So this is that just kind of mapped into a compressed view. So this looks like a good fit. I won't do the power law because it'll take a bit too long. But you would see with a power law, if you do it on your own, that you would get kind of an S shape here, showing you that the model is not reproducing the data very well. Okay, so that's kind of the basics of doing an X-ray analysis, the simplest kind in 3ML. Any questions quickly on that? All right. And so one other thing that I wanted to touch on is that if instead you wanted to do something like model your background with a function, it's also possible to do this. So I've made another simulated data set. Don't worry about the details. I've gone and selected some channels, rebinned on the background. We can look at, here I've changed the axis to being linear. Same kind of thing as before. And here I do a composite model, which is just power law plus a Gaussian. I'm looking for some kind of line. I put some priors on the line, build a point source, build a model, very similar. Let's crank down the live points for now. Now I fit in multi-nest. And when I do that, since I'm using a background observation, it does the profile likelihood. So multinest is going to go through and fit that. And just, yes, if you were to put this in a script and run it with MPI, any of the fitters that use MPI, that works just like they normally would. So you could make a script and then run it with MPI exec, and everything would run a little bit faster sometimes. So I got my fit, and as you see, since this is an additive model, it's power law plus some line. The parameters are underscored with each other, and it's instead of saying main.spectrum, it says main.composite. We could go through and plot the different components of that. I don't have time to go over that now. We can look at our fit in the data space. I've just changed, again, the data color and the model color here. But perhaps we wanted to have a better estimate of the background. We could also make a model for the background. And so the way to do this, and this is in the documentation, is that I do a spectrum-like, which is the much higher in the class hierarchy from OGIP-like. It's a bend histogram, but it doesn't have a response. So typically, right, our background's not really going through the response the same way that our observation is. It varies from instrument to instrument, but that's how we're going to treat it here. So what I would do is I would take my Chandra plugin that I built that already knew about the background from the background file, and I would make a new plugin, a spectrum-like plugin called from background. Would give it a name, and I would tell it which plugin that I wanted to extract the background from. And you'll see now it says, okay, this is just my background spectrum, and it's got, and it's just Poisson distributed data. Then I would build up the model that I wanted to use for my, to model my background. Here it's power law with some various Gaussian lines on top of it. And I would build a model, and then I would set that model to the plugin. And then I would have a background plugin. Now I would have to reload my Chandra data, but this time, instead of setting the background equal to a file, I would set it equal to this plugin. And what you will see when you go and plot the spectrum is actually that background model up against the total data. So what it's doing is it's kind of overplotting these two different plugins. One of them holds the total data and just thinks about it as Poisson distributed data, and the other one holds just the background data, but with a model folded through it. It's not the greatest plot in the world, but that's kind of what's going on. And what happens is in the background, the Chandra plugin, so plugins can also have local parameters that they know about themselves. So one of them is like an overall correction parameter, which you can free. I don't have time to go into that here, but this is like a constant multiplied by the response if you wanted to do some kind of calibration or inter-instrument calibration. But what's going on is the model that's associated with the background plugin has gotten passed to the main Chandra plugin's nuisance parameters. And it's just allowing the two plugins to talk to each other. And since there's already priors set on them, you can see here like that already has priors. I could do a Bayesian fit. Again, I'll run out of time. I choose multinest. And I would do background upsample. It's a 9-parameter fit, so it might take a bit. And it would fit, what it'd be doing is fitting the total spectrum to the main plugin, while at the same time optimizing just the Poisson likelihood for the background model on only the background plugin. So that's how we handled background modeling for the OGIP-like plugins. It's different for Fermi, for like Fermi-Lat or Hawk or some other thing, but this is just the approach that you would use if you wanted to do that. And yeah, this will probably take some time. And there you, yeah, the rest of it is just, I don't want to bump into Chandra's, to the Sherpa demo. So yeah, if you finish running this example, I doubt it will finish soon, then you can display the fits to the overplot that fits to the total source in the background and see that, wow, it's actually finished. Interesting, yeah, so we optimized all those parameters. So you can see here, here's the parameters for the background. They're not associated with the main source. And very quickly, oh, That's a very large corner plot. Yeah, so I used the configuration to change the style of the corner plots just for fun. And then we could see the overplotted fit to the background spectrum and the, here, the background. They're not using the area scaling in this plot. But yeah, that's just a simple demo on how to do that. Yeah, I won't have time to go to the advanced topics. There's some stuff on simulating fake data in the tutorials, and also how to, so if you wanted to make your own, which is what I did, your own observations, just to play around, test some models, etc., which is what like things like the PPC tools are using. There's also some stuff here for like how to access samples and make some of the plots that we have helper functions to do, but if you wanted to go through and make your own trace plots, how to do that. I won't get a chance to go over this in the time remaining, but if you go over the advanced stuff, we show how to do photometric fits. So we have a plugin for that. It doesn't use like a unity response. It actually folds the model through the filters if you have photometric data. And this shows you how to do a joint X-ray photometric data fit using some data from Grand, and then how to build more complex models that have like linked parameters. If you have, say, you're fitting 2 white dwarfs and you know their temperature should be the same, but maybe their overall intensity is not, you can link those parameters and fit all the data together. So yeah,